Our plan for today, I'm going to start by taking questions. As usual, I imagine there might be a couple of questions on maybe those last problems on the assignment that we're turning in today. And then we'll work on finishing that section that we started last time. If we have time, we'll get started on the next chapter. I've got those to hand out here, and in Williston, over on the side of that table on the side of the room, there's two piles, one that has the notes for the next two sections. And I've got those to hand out today. Also ready today is that first test that we talked about. I talked originally about having that test due this Friday, but that was when I thought I'd be able to post it by last Friday, which I wasn't able to finish writing it then. So I pushed the due date out to a week from today. I've got that posted. I also have hard copies to hand out, so you don't have to worry about printing that one out. In Williston, those are in the manila envelope on the table, so you can grab one of those, sometime before you leave class today. Before we begin new stuff, or finishing new stuff, are there questions? I'm sure there probably are on the assignment that you're turning in today. Everybody's all set with all of the problems that are on the assignment that you're turning in? Oh, I see, yeah, that was from earlier. I have the chat window in front of me here, and that was just them asking about sound. Numbers 5 and 6 are okay? Okay, so some questions on number 6. So we start with, was it 50 grams?
Yes, 50 grams of salt.
And a 200-liter tank?
Yes.
In our inflow, our goal is 1.5. It's 1.5. There was and in the beginning it said 1.5, and then in class yesterday I corrected the typo at the end, said 0.5. So it should be 1.5 grams per liter. So our inflow is
2.5.
Yeah, 2.5 liters per minute, and that is at 2 grams of salt per liter. And the out 3 liters per minute, and the concentration is whatever the concentration is at the time, right? Like as this happens, the concentration of the tank is changing. So our dx dt is our overall rate of change of the amount of salt is the rate in minus the rate out. And so we have 2.5 liters per minute times 2 grams per liter minus the rate out at 3 liters per minute times whatever the amount is, x of t over the volume, v of t, grams per liter. Now the volume is changing because it's flowing out faster than it's flowing in. It's losing half a liter per minute. So our volume function is just 200 minus 1/2 t. Is that okay so far? So the first, that's just 5 minus, and then 3 times x of t over 200 minus 1/2 t. So when we write these, this is a linear equation because we could think of it as, on the other side of that equation, we just have a function of t times x. That function of t is this piece right here. So I'm actually going to kind of just pull out that and write as a single factor out in front, which sort of look more like the linear factors that we've been working with. So 3 over 200 minus 1/2 t times x. Now you could leave it this way, but I find it cumbersome to have fractions within fractions. So what could we do?
Multiply everything by 2.
Yeah, the top and the bottom of that fraction multiplied by 2. And then to write it in that standard form for a linear equation, usually we grab the x with the x prime factor, or the x prime term. So we have dx dt, which I'm going to just write as x prime now, plus 6 over 400 minus t x equals 5. Now, oops. And I did one other thing, and I don't know that it necessarily matters, but I found it worked out well when I did it. I didn't actually try it the other way around, but I found it a little bit easier to work. I like starting my linears with t, like a positive t. If I'm subtracting, I want to reverse the order of subtraction here. So I just pulled out a -1 and changed that sign to compensate. So I just called this x prime minus 6 over t minus 400. I don't know that it's necessarily like that makes much of a difference, but I'm just in the habit of doing that, so I did. So hopefully, we've gotten to a point where we have our linear equation that models it that looks something like this. It's not separable, I don't think, but it is linear, so we have another technique we can use, right? What can we do with this? Integrating factor? Yep. So our integrating factor, mu of t, is e raised to the integral of this function of t here, right? Which we have to grab that negative sign with it. So that would be minus 6 over t minus 400. Maybe drag the -6 out. What is that integral?
It is 6 times natural log of 400 minus t.
Mm-hmm.
Well, that's everything.
Or t minus, yeah, okay, so you could probably do it the other way around too. But yeah, so, and that's convenient. What is this going to reduce to? Like, that'll simplify it pretty nicely, right?
Be t minus 400 to the -6th.
Yeah, in fact, so that's exactly right? So we have this factor in front of the ln, so that can be brought up here as a power, and then e raised to ln of stuff is always just the stuff. They annihilate each other, they're inverses. So this is t minus 400 to the -6 power. And so if you now just multiply both sides by this, you should find that that left side is the derivative. It looks like what you get if you use the product rule to differentiate x times mu of t, our integrating factor. So then you just say, oh, I'm integrating the derivative, and those undo each other. And then the right side is a power rule integral. The rest of it, I think, really mostly comes from being careful with your algebra. So you can get the x of t and find that constant of integration, because when you integrate, you'll have a constant of integration on the right side, and use the fact that x of 0 is 50, and you could find that constant of integration. And then for part 2, for the second part, just answering the question, once you find your x of t, there's the overall question we want to ask is, well, the question they ask ultimately is, will it reach the desired concentration before the tank empties, right? Because we know that we're losing half a liter per minute. So I think we need to find when the concentration reaches 1.5 grams per liter, and then from there, see however long it takes, what is the volume at that time? Because we have a volume function, right? 200 minus 1/2 t. See if we still have water in the tank. So the key comes from when you're, or at least some of the trickier algebra comes from setting, x of t over v of t equals 1.5. So that tells us when does the concentration reach 1.5 grams per liter. Then find the volume of the tank at that time. I think that when I did it, I found a time of around 80 something. So you might check that result. Again, I don't want us to focus too much just on the final answer, but that'll give you like something to kind of compare against if you're like way off. I was able to do this without really having to make any approximations in my calculations until the end when I was actually calculating the time. It wasn't that cumbersome to pull down the exact values that I found. And that helps. I think that when if we start rounding early on, that can kind of compound into making our answer a little bit less accurate. How's that? Other questions? No? Okay. All right. If there aren't any other questions, then we'll kind of pick up where we left off. We had been working on how we solve these non-homogeneous first-order linear differential equations. So the homogeneous ones, those were the ones that are separable, and we could use a integrating factor or just separate the variables. To solve a non-homogeneous ones, we needed to use an integrating factor, or we learned there's another way to go about it. Basically, if the function on the other side of the equation is non-zero, then based on what that looks like, we get a form for like what our best guess is for the form of the particular solution. So if it were e to some stuff, then our particular is just some arbitrary constant times e to the stuff, the same thing, right? So here is our, what we call the forcing function, and then here was our best guess. And then we just substitute it into the equation. Here we're just making sure that x prime plus 2x is equal to e to the negative 3t. And this is what we get when we make that substitution, and it allows us to solve for that unknown constant up in front. We had to first find the homogeneous solution always, because it's really important that the homogeneous solution, that we just note that if it's the same as the forcing function. And here they're not the same, right? Those powers on E are different. That's super important. So because the powers on E were different, we just said, okay, it's just some constant times e to the negative 3t. We find our particular solution, and then our general solution, here's the sum. You take your homogeneous solution plus the particular. Now, what if the forcing function is the same? as the particular solution. So here's our forcing function, e to the negative 2t. Again, I'm just going to rewrite this equation. It was x prime plus 2x. Now it's equal to e to the negative 2t. Our homogeneous solution that we already found was c, some constant c, e to the negative 2t. It's the same form, right? The forcing function is the same as the homogeneous. So in this case, our x particular cannot be some constant a times e to the negative 2t. We have to throw in a factor of t, basically how that works. We won't see this until we get into second order functions, I think, but if t times e to the negative 2t was already a particular, then what we would do is add a t squared. Basically, you add whatever power of t, the smallest power that's not already included in the homogeneous solution. So our x particular that we're going to start with is some constant a times t e to the 2t, or negative 2t. In order to help us figure out what that value a has to be, we're going to find x prime and then substitute it into the equation to make sure that this equation holds. Find out what value of a makes the equation hold. So define x prime. What do we need to use? Yep, we're going to find the derivative. How do we get the derivative of this function?
Chain rule?
The chain rule will be used, yeah, but that's not the overall like first thing that we need to focus on. We can't split up a derivative over multiplication.
Product?
Yeah, it's a product, so we need to use the product rule. So let's say derivative of the first, so if I kind of think of these as my two bits here, at and then e to the negative 2t. Derivative of the first is just a times the second, e to the negative 2t, plus at times the derivative of the second is minus 2e to the minus 2t. So there's the chain rule at work. I'm going to simplify this. Oh, whoops, that's prime there. That's a derivative. So, so what's left is to substitute this into the equation. So x prime plus 2x equals e to the negative 2t. So that's going to look like this. This simplifies pretty nicely. We have a positive 2at to the negative 2t and a negative 2at to the negative 2t, so those cancel. And we get a e to the negative 2t is equal to e to the negative 2t. So it must be the case that a is equal to 1. And that gives us our particular just t e to the negative 2t. Now we're not quite done yet. We want the general solution. So our general solution x of t is the sum, the homogeneous plus the particular. So we have some constant c e to the negative 2t plus t e to the negative 2t. We could leave it like that, or some people like to factor out the e to the negative 2t. It's really up to you, I guess. Questions on that one? Okay. Then let's try another. Here. Oh, yeah. Sorry about that. All right, so now we're changing our forcing function to sine of t. It's the same differential equation, right? So we've got x prime plus 2x equals sine t. Our homogeneous solution that we already found is equal to c e to the negative 2t. Clearly, the forcing function is not the same as the homogeneous solution. When the forcing function is a sine or a cosine or some linear combination of sine and cosine, then our particular is a linear combination of sine and cosine. So some constant a times sine t plus some constant b times cosine t. I've heard it put this way, that when you're coming up with your kind of guess for, like, here's the basic form of the particular, is you take the forcing function and all of its derivatives. That sort of holds. It kind of falls apart a little bit when we have to add in the factor of t. But when you think about it, it kind of makes sense, right? So if it's the form e to some stuff, its derivative is just e to some stuff. If it's the form sine and cosine, sine or cosine, like, you need sines and cosines in there if you got all the derivatives. So our next step is we're going to find the derivative, xp prime. What do we get?
A cosine.
Can you turn on?
A cosine t minus b sine t.
Yep. Great. So now we have x, and we have x prime. We're going to substitute. At first, an equation like this might seem odd or challenging, or just thinking about solving it, just because we have a single equation and two unknowns. But when you're working with sines and cosines, the way we approach it is we just say, oh, well, we're going to simplify the stuff on the left. So that means that the coefficients on sine have to be the same, and the coefficients on cosine have to be the same. We actually do kind of get two equations out of this single equation that we have. So I'm going to start by distributing that 2. And then I'm going to gather my like terms. I'm going to gather my sines together and my cosines together. So look at the sines here. So here's my sine and a sine. So overall, my coefficient on sine on the left is 2a minus b. And then my coefficients on cosine are a plus 2b. So on the right side, we just have sine of t. Really think of this as 1 times sine of t plus 0 times cosine of t. That allows us to compare coefficients so that 2a minus b has to be equal to 1, and a plus 2b has to be equal to 0. You could take whatever your favorite technique is for solving a system of, linear equations, 2 equations and 2 unknowns. I think a substitution would be pretty simple. So let's see, a is equal to negative 2b if I use the second equation. And we could plug that in. So on the left here, I think we get a negative 5b equals 1. And so b is negative 1/5. And we already know that a is equal to negative 2b. We use that to make our substitution, so a is going to be a positive 2/5. And that gets us our particular solution. Let's see, it was of the form a sine t plus b cosine t. So 2/5 sine of t minus 1/5 cosine t. How's that so far? Okay. And now, putting all this together, our solution is the sum of the homogeneous in particular. So we have some constant c, e to the negative 2t, plus 2/5 sine t minus 1/5 cosine t. So when we find this x of t by saying it's the homogeneous plus the particular, we call this the general or complete solution. I'm putting these two together. It's the same solution you'll come to if you use an integrating factor, but it's a bit more algebraic approach. And it's an approach we'll find particularly useful when we look at some second order differential equations. Questions on that example? Okay. And of course, we might be asked to solve some initial value problems, meaning if they give us a value, in this case an initial value for x, given at t equals 0, let's find the actual particular solution for that given initial condition. So we've already solved this one. I think this was part A. And we found the general solution was c e to the negative 2t minus 1/2 t, plus 1/2 t minus 1/4. So I'm going to start with that. And now we just want to figure out what that constant is, so we'll plug in our known value. So we get 1 equals, if I plug in t 0 for t, then c e to the negative 2t, that's just a constant c. And then the 1/2 t goes away, so we just have minus 1/4. And we get 5/4 is equal to c. Questions? Practice exercises for this material here, where we're coming up with that x particular based on what the forcing function looks like. They're posted to Canvas. Those you won't find in the book if you've managed to get a copy of the book yet. But if you go to the modules and click on today's material, there is, it's posted on the previous one because I thought we were going to get to it then. Posted under Wednesday's stuff, and it will be posted. I'll link to it under today's stuff too. But anyway, the PDF is there. Questions before we talk about second order equations? Okay. Give me just a minute here. I'm going to hand out these notes to the folks in Randolph and in Williston. Again, you should see 2 piles over there. One, you could take them both. That'll cover us for the next couple classes at least, I think.
Still, like you.
Just so I don't forget, I'm going to hand out the second section. We won't get to these today for sure, but you'll have them on review.
God, it's just too far.
Okay. So today's this second order stuff. There's a sum, like the practice exercises. There's a few in the text if you have the text, and it'll be posted. I'll post the exercise pages like I did before for those who haven't been able to get a copy yet. Also, additional exercises in a handout that's posted to Canvas. Our approach to these is very similar to what we did just in this last section. So we're looking at second order linear, ordinary differential equations. We're starting with a homogeneous, and in fact, pretty quick, we're going to focus on ones with constant coefficients. But just first, any linear equation is one where you're multiplying any factor in front of the x prime or in front of the x is just a function of t, not a function of x. So this is linear because I could think of 25 as just a constant function of t. It's not like x squared or square root of x or sine of x or anything like that. And on the other side, it's just a function of t, right? So I don't have x's over there. It is linear, but not homogeneous, because homogeneous has to be set equal to 0. This one down here is homogeneous and linear, right? So I've only got functions of t being multiplied by x prime or x, and it is, in fact, set equal to 0. So one result is that if you have a couple of functions that are solutions to a linear homogeneous, it's important that it's both linear and homogeneous. We've got two functions that are solutions to a linear homogeneous differential equation, then any linear combination of those two functions is also a solution. So what is meant by linear combination is you could take each of those two functions, multiply them each by some constant, their own constant, right, and add them together. That's what a linear combination is. And a linear combination of x1 and x2 would take on this form. You know, if C1 and C2 could be any old constants they want to be, some constant times x1 plus some constant times x2, that's a linear combination of x1 and x2. So if you have functions that are solutions, any linear combination of those functions is also a solution. We can verify in this particular example, x double prime plus x equals 0, that these functions are solutions to the homogeneous linear differential equation. So let's start with that. So we have our two functions, x equals cosine t and x equals sine t. We'll verify that individually they're solutions to this equation. So if x is cosine t, that means x prime is negative sine t, and x double prime is going to be negative cosine t. So if I take x double prime plus x, which is the left-hand side of that equation, we get negative cosine t plus cosine t. That is, in fact, always equal to 0. So that's a solution. If we do the same thing for the other function they gave us, x is equal to sine t, we need the second derivative. So the first derivative sine is cosine, and then its derivative is negative sine. And now we'll just plug that in to the left side of the equation. X double prime plus x looks like negative sine t plus sine t. That is, in fact, always equal to 0. Whoops. So here we have, verified that each of these two functions on their own is a solution to this differential equation, which is both linear and homogeneous. And Theorem 1 tells us that any linear combination of these two functions is a solution. So I can make a function x of t as any old constant, say c1 times cosine t plus c2 times sine t, and that will be a solution where c1 and c2 are any real numbers. Questions so far? Okay. If we change this equation slightly, we look at x double prime plus x equals 1 instead of 0. We could verify that these two functions that they gave us, x equals 1 plus cosine t and x equals 1 plus sine t, are solutions. And it'll, won't take very long. If x is 1 plus cosine t, then x prime is negative sine t, and x double prime is negative cosine t. And so if I take x double prime plus x, I have negative cosine t plus 1 plus cosine t. And what does that reduce to? Just 1. So that is, in fact, a solution to this differential equation. It does, in fact, equal 1. Take this other function. If x is 1 plus sine t. Then x prime is cosine t, and x double prime is negative sine t. If we plug these into the left-hand side, we get negative sine t plus 1 plus sine t. And again, everything cancels except for the 1, so we're left with x double prime plus x equals 1. That's a solution. However, this equation, x double prime plus x equals 1, is non-homogeneous. So that means theorem 1 does not apply. We cannot conclude that any linear combination of these two functions is a solution. Questions? Okay. All right, so here we're returning to some terms that we've already learned before, but if we have an initial value problem, it's important that the two values they give us one for, x of t naught and x prime of t naught, one for the function and one for the derivative of the function, and they're given at the same value of t. In order for it to be an initial value problem, they have to be given at the same value of t, otherwise it's just called a boundary value problem, and those are a little bit harder to solve. And so this allows us to find these this particular solution, these unknown constants that we might need, right? We know that any linear combination of x1 and x2 could be a solution to the differential equation, but if I have some initial values, some values given that allow us to find what particular constants those need to be. So we're going to solve this initial value problem, and they're starting us off with x double prime plus x equals 0. This is the equation we were working with on the previous page. So we know from the last page that x is c1 cosine of t plus c2 sine of t from example 3.3. So we're going to use these initial conditions. If x is c1 cosine t plus c2 sine of t, we could find the derivative of that function. which would be what, negative C1 sine t plus C2 cosine t. And now we just plug in the values they gave us. X of 0 is equal to 3. That means 3 is equal to C1 cosine of 0 plus C2 sine of 0. Ready? Okay. So sine of 0 is 0. Cosine of 0, what's that? 1. So we get 3 is equal to C1. X prime of 0. Let's see, it gives us, let me finish writing the equation. X prime of 0 is 3.5. Means 3.5 is negative C1 sine 0 plus C2 cosine 0. Again, sine of 0 is 0. Cosine of 0 is 1. So we get C2 is equal to 3.5. And now our function, we just throw those values in. So C1 is 3 cosine t plus 3.5 sine t. Questions? Okay. If we found a pair of functions, x1 and x2, that are what we call linearly independent. And so if you have just two functions, linear independence just means that one function isn't just a multiple of the other function. If you have those two functions, and it is the case that any linear combination of those two is a solution, then those two functions, x1 and x2, are called a basis for the differential equation. And I have to apologize for the bad line break here. So equals 0, I can fit the whole equation on one line. So from example 3.3, we can conclude cosine t and sine t, they're a basis for the differential equation x double prime plus x equals 0. We're going to verify that e to the t and e to the negative t are a basis for x double prime minus x equals 0. And we can do that just by plugging them in. For a second order differential equation, your basis will be just two functions. So I'm not worried about missing some third function. So our x function, let's see, let's start with e to the t. If x is e to the t, x prime is just e to the t. So x double prime minus x is e to the t minus e to the t, which is, of course, 0. And if x is equal to e to the negative t, x prime is negative e to the negative t, and then x double prime is, again, positive e to the negative t. And it takes a couple seconds to realize that, of course, this also turns out to be 0. And e to the t and e to the negative t are not multiple, one is not a multiple of the other. They are linearly independent, so they do form a basis. And that means that any solution to this equation is going to be of the form some linear combination of these two. So C1 times e to the t plus C2 times e to the negative t. Any solution to this homogeneous equation looks like has that form, and they gave us some initial values here. So now we're going to figure out what C1 and C2 are. So I'm going to go ahead and find the derivative. X prime of t is C1 e to the t minus C2 e to the negative t. And now we'll plug in our initial values. X of 0 is equal to 6. That gives us 6 equals C1 plus C2. And if x prime of 0 is equal to negative 2, that gives us negative 2 equals C1 minus C2. You could take your favorite way to solve a system of two equations and two unknowns, but I feel like this one is just begging us to use elimination by addition, because if we add these two equations together, those C2s just cancel each other right out, and we get 4 is equal to 2 times C1. And of course, 2 is equal to C1. And if 2 is equal to C1, use either of those two equations above, but you'll find that C2 has to be 4. And so that gives us this function as our general solution to the homogeneous equation, or particular solution to the homogeneous equation. Questions? Okay. All right. So we're going to focus now on these linear, second order linear ODEs with constant coefficients. And we talked about characteristic equations in the last section with those first orders. It was, in the last section, it was really just like, oh, hey, here's another way we could do these equations that we already have other ways to solve. Like, if they were homogeneous, then they were separable anyway, so we could separate the variables. Or even if they weren't homogeneous, we could use an integrating factor. Now we're going to find the characteristic equation to be particularly helpful to help us solve these second order equations. So a second order equation that looks like this, x double prime plus ax prime plus bx, has an associated characteristic equation that looks like that, r squared plus ar plus b equals 0, where the coefficients on this quadratic come directly from the coefficients on that second order equation. We know how to solve quadratic equations, and we know that one of three things is going to happen when you solve a quadratic. You're either going to get two distinct real roots, you're going to get a repeated root, like maybe your quadratic is just a perfect square anyway, or maybe there are no real roots, maybe the roots are complex, and so the roots are complex conjugates of each other. If you have distinct real roots, this is a scenario where we call it that is called overdamped. And if you have distinct real roots, a basis is e to the r1t plus e to the r2t. So whatever the solutions are to those to the quadratic, whatever the roots of the quadratic are, tell you what those exponents on e are going to be. And so your solution is just a linear combination of those two. If you have a single real root, like a repeated root, like x minus 2 or r minus 2 squared, right? So like 2 would be a repeated root. Then we call this critically damped. And a basis is e to the RT and t times e to the RT. So your solution is a linear combination of those two. And then if you have complex roots, like alpha plus beta times j, alpha plus or minus beta times j, this is called underdamped. And your basis, the real part of the complex root, like the alpha part, tells you what the coefficient is on t and the exponent on e. And then the imaginary part is the coefficient on t in the argument of cosine and sine. So your basis is e to the alpha t cosine beta t and e to the alpha t sine beta t. So we're going to get a little practice. We probably won't finish this section today. We'll get a little practice finding general solutions. We're going to start with a familiar example. We looked at this one on the other page and already kind of verified what a basis was going to be, but we're going to see how we arrive at it ourselves using the characteristic equation. So the characteristic equation for this ODE is r squared minus 1 equals 0. Notice that there's no x prime term, so there's no r term. This is a difference of squares, so we could factor it r plus 1, r minus 1. And that gives us r equals negative 1 and r equals 1 as roots. So this is overdamped. And that means that the general solution for this homogeneous equation, our basis is e to the negative t and e to the t. So the general solution is a linear combination of this, c1 e to the negative t plus c2 e to the t. Questions? Okay. Let's try another. So this one, we're kind of thinking about it backwards. They give us the basis, e to the negative 2t and e to the negative 3t. And we want to find the differential equation that has that basis. So when I start with the basis, first of all, there's no factor of t in front of e, right? It's just e to the negative 2t, e to the negative 3t. So what that tells me is that the characteristic equation has distinct real roots that are negative 2 and negative 3. And if this roots are negative 2 and negative 3, that must mean that it would factor as r plus 2 times r plus 3 equals 0. Let's FOIL this out. We get r squared plus 5r plus 6 equals 0. And once you have your characteristic equation all multiplied out, the ODE just kind of falls out of that. What should the differential equation look like?
X double prime plus 5x prime plus 6 equals 0.
Plus 6x equals 0. Yeah. Good. Questions? So the coefficients on the characteristic equation directly translate to the coefficients on your x double prime, your x prime, and your x in your differential equation. Let's try another one. Okay, so now the basis looks different. We have e to the negative 2t and then t times e to the negative 2t. What does that tell us about the characteristic equation? Let's go back up to this table.
Single real root.
Can you say that? Can you turn on your microphone?
It's a single real root.
Yeah, a single real root. So we're in this situation here, the middle row. That means that we have a repeated root. And that root is negative 2. So our characteristic equation looks like r plus 2 times r plus 2. Multiply this out, r squared plus 4r plus 4 equals 0. And now what is the differential equation going to look like?
X double prime plus 4x prime plus 4 equals 0.
Plus what?
Plus 4x.
4x, yep. Okay. Ready for more? All right, let's solve this initial value problem. X double prime plus x prime minus 2x equals 0. So the first thing we can do now is just find that characteristic equation. You know, we're turning this mostly from one that makes us think about derivatives and integrating and, you know, maybe integrating factors to more of an algebraic problem, which is kind of nice. It's a kind of familiar and more comfortable domain. So what is the characteristic equation for this differential equation?
Just distinct from real root.
Well, maybe. I mean, we don't know whether we have distinct real roots or not because we haven't written out what the characteristic equation is.
Is it r squared plus r minus 2 equals 0?
R squared plus r minus 2 equals 0. Yeah. And then, you know, take your favorite way to solve a quadratic. I like factoring or completing the square. I think this will factor. What do we get?
R plus 2 times r minus 1?
Mm-hmm. So we do have distinct real roots. So r equals negative 2, r equals 1. And that means that our basis for a solution is e to the negative 2t and e to the positive t. So now our general solution to this homogeneous equation is C1 e to the negative 2t plus C2 e to the t. It's any linear combination. If they hadn't given us some initial values, we'd be done right now. We couldn't go any further, but they did give us a set of values. We know that x of 0 is 4, and x prime of 0 is -5. So let's go ahead and find x prime of t, and then we'll plug in, use these initial conditions and try to find C1 and C2. So let's take derivatives. Mostly just the chain rule we have to worry about here. So we get -2c1 e to the -2t plus c2 e to the t. And if we use the fact that x of 0 is equal to 4, what equation does that reduce to?
Is it 4 equals -2c1 plus c2?
That's x prime. So use the x function.
Equals c1 plus c2.
Yeah, C1 plus C2. Now go ahead and use, since your mic is already on, I'm going to put you on the spot. What does it look like if we use the fact that x prime of 0 is equal to -5?
Be -2c1 plus c2.
Yeah, and that's equal to -5. Cool. Again, take whatever your favorite way is to solve a 2x2 system of linear equations. I like elimination by addition, so I'm just going to note that C1 and C2 have the same coefficient. So I'm going to leave the top one unchanged, and I'm going to multiply the bottom one by -1. So we get 5 equals 2C1 minus C2. And if we add these together, the C2's cancel. We get 9 equals 3 times C1. Or C1 equals 3. And if C1 is equal to 3, what is C2? Yep, just get 1 for that. And now we've got the particular solution to the homogeneous equation. Questions on that example? Okay, so is this equation, is this an overdamped, critically damped, or underdamped? And how do we know?
Is it overdamped because it has a distinct real? It has 2 bases?
Yeah, right. So there were 2 distinct real roots. This is how we know, right? I had 2 different roots that were both real numbers, so that's an overdamped system. When you have a repeated root, that's critically damped. If your roots are complex, that's underdamped. I'm going to leave it there. We're pretty close out of time. I don't think we have enough time to get through the next example. So we'll pick up where we left off on Wednesday. Please bring any questions that you have. And I have a hard copy of the test to hand out to folks here. And if you haven't done so already in Williston, in the manila envelope on the table on the side of the room, you can find a hard copy of the test there. Keep in mind, before you guys take off, tests are done independently. The very first page of the test is a reminder of the rules and a signature where you're going to sign that you understand and that you've agreed to follow those rules. You should read and sign that first before you start working on them. It's okay to ask me questions. It's okay to ask Jason Lacrosse questions down here in Randolph, and I'll let him know that that's coming, but it spells it out right on the first page of the test. So if you get stuck, start early, ask questions early, ask questions often. I'm going to begin class Wednesday, seeing if there are questions that you have. I didn't make it super hard because it's take home. Like I didn't take advantage of that opportunity. But I'll see you all on Wednesday.
Just like straight.
Hard copy of the test?
Yep, I've got that coming.